Hey guys, we're in section 8.4 on pages 16 and 17 in the notes. You can see here we're testing for the difference between proportions, and I've given you the big ideas before that data comes in two types, quantitative versus qualitative. So if we have qualitative data, we'd be back to being interested in proportions. And if we have two independent samples, we'd like to compare two proportions. If a claim is made, we're going to be doing a two-sample z-test, and three conditions that we usually check would be that the samples are random, the samples are independent, and they're large enough to use a normal sampling distribution, meaning each of the NPs times NQs for each of the samples must be at least 5. So when those conditions are met, we use p hat 1 minus p hat 2 to help us test the difference between proportions. Some of the theories behind this is that the mean of the sampling distribution will equal the true difference in the means. And you're going to see that when we go to create a test statistic, we're going to have to assume the two proportions are equal for the populations. So that means we're going to go into the samples and pool the number of successes together. So we get this thing called the weighted estimate. We call it p bar. And when we do so, the standard deviation quantity that's in the denominator of our test statistic is going to use p bar, q bar, and then the sample sizes as such. Okay, so once we go to get the p-hats from the data, we'll have that z statistic that we're able to calculate. And we'll do so as long as each of these things are at least 5. I'm not going to read out the 8-step process I have here, but it takes about 8 formal steps to do a hypothesis test for a difference in proportions. So let's go check out those 8 steps in an example on the next page. Alright, so our first example of doing a two-sample z-test for a difference in proportions, we've got a study with 150 randomly selected occupants in cars and 200 occupants in trucks. And we simply looked at the proportion who were wearing seatbelts. In cars, it was 86%. In the trucks, it was 74%. So at alpha equals 0.10, can I reject the claim that the proportions who wear belts is the same in the cars and the trucks? Okay, so step 1 is to summarize the data. So when we go to summarize our data in step 1, I'll try to name the steps for us. So summary stats. We are comparing two independent samples with cars and trucks. And for the cars, we've got a sample size of 150, and we got a p-hat at 86%. We'll call truck sample 2. The sample size is 200, and we have a p2 hat at 74%. Okay, now, in order to get the pooled estimate, and if we were to do any calculator shortcuts, we're going to need to know how many people said, yes, I was wearing a belt in each sample. So we'll just use the letter X for that. So that would be 86% of 150 people, or 129. So we have 129 people who said yes, and therefore we'd have 150 minus 129, or 21 people who said no. Okay, and then for the second sample, we need to know how many people said yes. So we have 74% of 200 people, which means 148 people said yes, and 200 minus 148, or 52, said no. All right, step 2 is our verify conditions. So we've got random and independent samples. All right, and then here's, all right, back up, erase. Forgot one part up here. To get p bar, the pooled estimate, I have to take the number of successes in each of the samples and divide by the total sample size. So we've got the 129 successes in the first sample, 148 successes in the second sample, and the sample size total at 150 plus 200. So if you do that math, p bar comes out to be 0.791. I usually like a little bit of extra accuracy there. And q bar is 1 minus p bar, so that's going to come out to 0.209. Alright, step 2, verify conditions. And that's where we need random and independent samples. Okay, and we need each of these quantities. Each of the quantities, n1 multiplied by p bar, n2 oops, sorry, I keep making mistakes here, n1 multiplied by q bar, n2 multiplied by p bar, and n2 multiplied by q bar. We have to check that all of these are at least 5. Alright, so if we work that out, 150 times 0.791, that's 118.65. 150 times 0.209, that's 31.35. 200 times 0.209, that is 158.2. And 200 times still making mistakes. This one was times 0.791, and then times 0.209, that's going to be 41.8. And you see here that these are all at least 5. All right. So those first 2 steps in this 2 proportion test, they can be a little tedious. Okay, sorry about that. Step 3 is to write the pair of hypotheses. There was a claim that the proportion of people in cars is the same as the proportion of people in trucks who are seatbelted. So that's the claim. It's an HO claim. Remember, that's important when we go to write the interpretation of the decision at the end. Step 3 is easy. They gave us an alpha level to use in the problem. The alpha level was 0.10. Okay, step 5, if we're going to calculate the z statistic, here's the equation. It's got a lot of parts. Okay, so I have the p-hats from the data minus the true difference in proportions over the square root of this thing, p bar, q bar, 1 over n1 plus 1 over n2. So if you plug in all the pieces, it's a 0.86 minus a 0.74 for the difference in the p-hats. Now the p1s and p2s themselves, if they're assumed equal, their difference would be 0. And then here we have our p bar, 0.791, multiplied by our q bar, 0.209, multiplied by 1 over 150, plus 1 over 200. Okay, so that's workoutable with your graphing calculator. I got a z-value of 2.73. Step 6 is our p-value step. We're back to using a standard normal z-test, not t. There's no degrees of freedom. We're doing a 2-sided test, so we'd be getting that tail area double twice. The probability of getting a z greater than or equal to 2.73. So that's twice the normal CDF of 2.73 on the 10,000 on the 0.01, and that worked out to be 0.0063. So that's a P-low reject HO. Okay, sorry, squeezing in here. And then step 8 is interpreting that decision. So their is enough evidence. Remember, HO is the claim, so it's reject the claim that the proportion who wear seatbelts in cars and trucks is the same. So, page 16-17, demonstrating the z-test to compare two population proportions. All worked out by hand. No special graphing calculator features. You'll see those in objective number 2.